So multifamily is one particular example of commercial development. It's the example that we had looked at in the most detail, in part because it's relatively easy. Multifamily is multifamily. There are relatively small differences between the different types of multifamily homes. Larger commercial development questions is a bigger picture, so we're going to look at a few case studies here. The big takeaways are that there's nothing fundamentally different about other types of commercial development from the multifamily example we looked at. The same type of technologies can be applied, the air and the ground source heat pumps. We'll talk a little bit about biomass down the road. The same types of economics generally apply. Heat pump technology, particularly in the area of large commercial buildings, has improved quite dramatically and allows for some very interesting advantages to be taken for optimizing heat flow. The heat pumps can meet that primary load, but it really is when you begin to think about some of the greater complexities in large commercial buildings that you really begin to see some interesting possibilities. So commercial envelope improvements, that when I approached this, my original assumptions were that it's going to be much harder to deal with commercial buildings than residential buildings. Residential buildings are relatively simple use, so it must be harder to do commercial spaces. It turns out that even though there are a great deal of variability between them, they do have some real advantages. In terms of the economics of the improvements. One is that they do have much higher ventilation loads. Mechanical ventilation is going to drive that air changes for your building, and therefore the insertion of heat recovery or energy recovery systems that can recover part of that energy can generally be done at lower cost than in a home where once you've tightened it up to a certain level, you have to add those mechanical ventilation systems that you wouldn't otherwise have had. Simple surface area to volume ratio, that a big commercial space has less surface area per volume than a smaller home does, and therefore envelope improvements can be made for a less cost per square foot of operational floor space. The other piece is that you can, depending on the nature of your systems, have high plug loads. If you have an awful lot of computers or other types of equipment running in your office space, all of that equipment is giving off heat that you can then recover and move around in your space if you can optimize it, and you can take advantage of those plug loads as part of your heating system. And when you look at what's possible, big reductions in the types of commercial spaces that we have around here are possible. These two slides were simply taken from Cornell's Climate Action Plan to give you a sense of what types of savings they're looking at recovering. So this is their office space. They were looking at about a 47% reduction in heating energy and a 16% reduction in the cooling energy. They already use highly efficient cooling systems, the lake source cooling, for a lot of their buildings, and so they have smaller reductions there. For lab spaces, as we think about high-tech or things like you might find up at the Cornell Tech Park that we'll talk about, even bigger savings are possible because these spaces are energy hogs. They use an awful lot of energy, and therefore they have bigger potential for savings. So they're looking at nearly a 70% reduction in the energy use from their laboratory spaces for heating and a 40% reduction in their cooling loads. And these are achievable. So I will give you a couple of quick examples of commercial spaces that have been built to what is called Passivehaus. Passivehaus is originally a German set of building standards, and the idea behind Passivehaus is relatively simple, that if you tighten the envelope enough, you actually cross over and begin to make it more economically efficient because you can undersize your mechanical systems. That the more tightly you build the envelope, the more efficiently you can then build everything else. So these next few buildings, they're all built by a single company down in Virginia, just to give you a sense of what has been done and what is possible. So this is a part of a K through 12 school. This is part of a public school system. It's the first K through 12 school built in the U.S. to meet the Passivehaus standards. It's about 3,000 square feet, completed back in 2010. The cost premium you can see is comparable to what we were looking at for our smarter building. It's a 3% cost premium. It's a 7-year payback, and with their annual energy savings of around $3,500. This building is actually a net energy producer because its goal is the Center for Energy Efficient Design that's meant to be an educational space. So it actually produces more power than it consumes. So it has the little solar panels here, it has solar thermal, it has a wind system that's just off picture, and so this building will actually produce far more energy than it needs. It has a ground source heat pump for the heating system. The kinds of spaces you can make Passivehaus, you wouldn't always think about them. This company apparently had done a lot of dental offices, so they were asked to make a Passivehaus dental office for these folks to leave to their kids. It's 5,400 square feet, and this was built for $155 a square foot. This company has built a number of these dental offices, number of conventional dental offices prior, and the construction costs in their area were $150 to $200 a square foot. So this is your normal fancy dental office, kind of reminds me of the Enterprise there. And it was built for $155 a square foot, so at the very low end of what their typical building costs were. Uses 70% less energy than a conventional dental office, and it does that in large part by some neat in-floor cooling through hydronic cooling system right around the dental chair. You've got the dentist, the assistant, the patient, the lights. That's where your heat load is concentrated, and so they pull that heat away from the chairs here and redistribute that throughout the rest of the building so they can get very high efficiencies. They have annual savings of more than $9,000 per year in terms of their energy savings. This one was kind of a neat space. This was a community space, so it has very, very different types of requirements. You might have 3 people in a room, you might have 300 people in a room, so you have to have an energy system that's capable of operating over a very large dynamic range. This is a fairly sizable building. It's 8,000 square feet. It was built for $135 a square foot, 60% less energy than a conventional construction. And this one is relatively unique because it was the first Passivehaus building anywhere in the world that we know of that actually had the commercial kitchen, including the hood and everything else inside the envelope. Many spaces actually will create a break between the kitchen and the rest of the building and allow the hood to be outside the part that's officially Passivehaus. This was able to put it inside. And probably the neatest example that they had was this dormitory. This is Hickory Hall on Emory and Henry College. It's the largest building in the U.S. To have achieved the Passivehaus energy standards. It is comparable, of course, to the type of multifamily homes that we were looking at. What was neat about it is that it has a nearly identical twin called Elm Hall that's just across the quad, literally just a few feet away from it. Elm Hall was LEED certified, and this building uses 60% less energy than that LEED certified copy of itself. Uses 74% less energy than the building code for Virginia would allow. So it does it by a combination of an improved envelope, ground source heat pumps, and energy recovery vehicles. And you can see some of the huge savings that you can get, how it is that you can begin to build some of these very high efficient designs without increasing the cost. So Elm Hall had a heating and cooling system that was 68 tons of capacity. The new Hickory Hall, when they built it, it was down to 14 tons for cooling and it was 12 tons for heating. And Hickory Hall is actually 11% larger than the Elm building that it was next to. And the neatest thing about all of this is they built the more efficient building for less money. When you look at the per square foot cost, Hickory Hall cost only just north of $118 a square foot. Elm Hall, which is a nearly exact copy of the building, was built for $125 a square foot just 2 years earlier. So these improvements don't have to add to the cost, and if you know that you want to do this from the beginning, you can actually find ways to bake in some of this to the process in ways that allow you to achieve these much higher efficiencies with comparable building costs. And you don't have to build boxy. I tried to stick with as many examples from the US as possible, but I can't help myself. This kindergarten is just too neat. Right, you've got big glass walls, you've got the wibbly wobbly roof, right? And this kindergarten here is built to full Passivehaus standards. They built the playground with a little ramp up on top and a green roof on the top of it there. You can do lots of neat things with these designs and still achieve very, very high efficiencies. You don't have to build rectangles. So this company that I was showing you those examples from, they were called Passive Science. And one of the things that they promote is what they call this integrated design process. One of the things that they really stress is that if you want to build high efficiency systems that are going to meet these kind of cost parities, you really have to start from the beginning. So they have this 5-step process, and I thought it was worth just running through some of the highlights of it. What they start with is to get everyone in the room at the same time, to get the owner, the architects, the engineers, get everybody together at the beginning and agree on what the goals are, what the budget is, what the decision-making process is going to be, who's responsible for what. Get the energy modelers started with the models as soon as possible and have everyone involved in an iterative process towards schematic design. The goal is to minimize future changes. What you want to have is as little as possible someone coming 3 or 4 steps down the process. Oh, wait a minute, you didn't leave me enough room for this, that the building wall isn't going to breathe properly and allow moisture to move. Go back and redesign this. Those change orders are where a lot of the extra cost in really high efficiency buildings come from. So the sooner you begin to integrate all of these people into the process, the better. The other reason to integrate the process is that you want to take full advantage of the undersizing that you can do for the mechanicals. So if you are spending all of this time and effort to design a very high efficiency envelope, you don't want someone to stick in a larger ventilation system, larger ductwork than they need, because that's going to drive that cost back up. So you get everybody together at the beginning towards schematic design. Then we come, of course, with the final design for the actual systems. When you have the electrical engineers and the mechanical engineers with the HVAC and electrical systems. You want to integrate the controls at the same time. The simpler the controls, the better. If you have people needing to program complex systems to make the building operate at high efficiencies, that's going to create more operational complexity. As much as possible, they like big buttons that you just kind of push, and that's all that you can do with it as an end user unless you really want to tear the system apart. Then you finalize the energy loads and the movement of heat and moisture through the buildings with the occupancy loads. Then you work with the contractors to finalize every piece. The pieces that come next are what happens during construction. Of course, you want to make sure everyone is fully trained. So for instance, EPA has these quality installation training inspections that you have to go through. It is often the case that when you would find problems down the road with these systems, they can be traced not only to design, but to installation and to commissioning. We'll talk about those as well. To conduct thermal imaging and blower door tests along the way. That way, if you find problems with the envelope, you can fix them before all the finishings have been added and you're trying to do these at the end. Again, the sooner you can make changes in each phase, the better it is for the overall cost. And then to commission and monitor the systems. That these systems, high efficiency systems, require them to be run properly. If people bypass all of your control systems because it's easier, you're going to lose all of that efficiency in the end. So you want to be able to monitor these post-system. This company monitors monthly for the first bit of time. It monitors quarterly for up to 2 years, and then out to 5 years it monitors annually to make sure that the buildings that they designed are actually performing as they should. So,
is that any different than what's done normally? The change orders, I would be happy to just shoot for no more than a usual number of change orders. Or do they normally test during construction? construction, whether systems are working?
It depends greatly on the nature of the builders. This integrated design process is certainly not the standard on all practices. I can tell you, for instance, it's not how the state goes through their design pieces. That bringing energy modelers into the picture early on is generally not one that we've seen in a lot of our building designs. The energy models are done only after the schematic design has already been done, and then we go back and try to horseshoe changes into the design. And so there are elements of this that I think different companies will integrate, and there's certainly different models for how you could go forward. I mean, it's one of the questions for the discussion that I was curious how people here view that kind of integrated approach and what models they've looked at. So these things can be built without having large cost premiums if you do integrate the design. Of course, we're not in Virginia, so I wanted to give you a few examples of these technologies working for us up here. SUNY Cortland, this is our new professional science building. This piece right here was new. It was grafted onto an older building, and this building was not designed to be high efficiency. This was originally the Cortland Overhead Door Company, and then was a facility storage shed for a number of years before it was turned into classroom spaces. The new construction is seen here. This is the old construction. It has a 40-well geothermal heat pump that's sufficient to provide all of the heat to the new building, or about a third of the heat to the combined system. And this gives you a sense of the size of the well field. It was drilled through our parking lot, and then the manifold is over in the grass for you to have access to those wells. We use the system in its kind of more complex way. So we have an energy recovery unit on the top that's fed by the heat pump system. So outside air is brought in and preheated, both by the existing air that's on the way out and by the heat pumps, big heat pump units. We have 3 large ones. But we also have 180 small heat pumps distributed throughout the building, and this is where you can optimize heat flow. So in many commercial spaces, you might have a south face that's getting a lot of direct solar gain that's heating up, and a north side that's getting very little solar gain and needs a lot of heat. And so in some buildings, you will find during the shoulder season that you may actually be heating and cooling different parts of your building at the same time. With heat pumps, you can move that heat around internally to the building and not have to heat and cool with exterior energy. So this was a day during early winter here in November. It was 18 degrees outside. As you would expect, most rooms were in heating mode. That's why this is red. But rooms with a large plug load, this is a data closet, so it was full of computer equipment. It was generating more heat than it needed, and so it needed to be cooled on that day, even at 18 degrees outside. So heat was being extracted from this data closet and moved into other rooms within the building. The upfront cost for our system, because this was all built within one large state contract, we don't have the separate numbers for the heat pump system. This represents our best effort to back out just those costs and the additional costs from what a conventional system would cost. So the green is what our ground source heat pump is costing us, and the red is what it would have cost us to heat and cool the building with, just heat the building, without the heat pumps. We have about a 12-year payback if you ignore cooling. If you add the cooling, because this space does have air conditioning, that moves back from there. And we generate about $100,000 in savings over 25 years and about a 7% rate of return on our investment. Other colleges have built these. Hamilton College, this is a dorm. It's the oldest LEED certified building in the US, shows that you can take a historic building and still do some of these types of retrofits. It has a 16-well heat pump, and it uses 60% less energy than it's made across the campus. You can build with lots of glass if you really want to. So this is the atrium of their science center. And that atrium is heated by a geothermal system on campus there. Locally, Cortland is not the only building, and it's not the largest. The new Peggy Williams Center up at Ithaca College, almost 60,000 square feet, completed back in 2009. It's a LEED Platinum building. has a heat pump system that's about 30% larger than the one that heats and cools Cortland. We haven't gotten the economic numbers for this yet, but it's one that we're wanting to take a much closer look at. Commissioning. It's very important that these systems, when they are, after they're constructed, that they actually be commissioned and monitored. So great care must be taken when you do this to make sure that you're actually going to get those efficiencies out of the system. The SUNY Cortland Professional Studies building, we found that for the first year didn't save us an awful lot of money. We had finally had the ability to hire an energy manager. One of the first things they did was look at this, and they discovered that our loop field hadn't been filled all the way. And so our loop field wasn't filled with glycol, and it wasn't producing any heat, wasn't pumping that heat out of the ground. Once that was repaired, it works much better. Argos in, they had a system that was put in, and when Tatum did commissioning on it, they found one example was a decorative cover had been placed over some of their little heat pump units, blocking the airflow that was supposed to come out of them, and that was hurting the efficiency of their system. The Lansing School District had one. The distribution system had been redesigned at some point after the heat pump was put in. The heat pump was working fine, but the distribution system that was designed didn't take into account some of the unique characteristics of that heat pump system, and that caused some issues that had to be resolved. So these systems do work very well when they are put in and once you get them up and running, but you do have to make sure that they're commissioned properly. The last thing we'll mention here is to just look at some of the options for even denser developments, commercial developments. This is the Cornell Business and Tech Park. Binoptics, that's over here. Binoptics was looking to expand and was one of the commercial entities in the area of this natural gas pipeline. So we looked at what you could do with these types of facilities. It's a fairly big facility, mixed laboratory production and office type spaces. If you wanted to go with a ground source heat pump, we wanted to know whether there would be enough room again in these developments. And just like we found with Village Solars, the parking lots are generally always going to be big enough for you to fit the well field. The well field to heat Binoptics, if you went just with space heating with ground source heat pumps, would fit comfortably under one of their two parking lots. When you need higher heat loads, when you need process heat pumps are great up to 110 degrees. If you need heat that's much hotter than that for steam, if you need much, much higher heat loads or heat loads that are spiked during very narrow times of the year, you can then begin to look at biomass. So Cortland's system is a hybrid system. It's not yet done with biomass. We have our ground wells here that feed into this part of our control loop, but we also have a boiler system here that can augment the heat from our ground source heat pumps. Right now, this is driven off of natural gas because the rest of the campus is, but our climate action plan envisions changing all of these out eventually to biomass boilers. So coupling biomass with heat pumps can allow you to chop off some of those very high loads and save money on your well fields. Can also provide higher heat for process heat. If you have big centralized loads, though, like the Cornell Tech Park, combined heat and power begins to look attractive. Middlebury College, for instance, has a biomass combined heat and power plant. And the idea there is you are producing electricity and then using the waste heat from that electricity as the heat source for heating your building. So you're getting two bites at the proverbial apple. You're using energy to make electricity, and then you're using that same energy as waste heat to heat your buildings. So this was completed in 2009. It's a fairly large construction. It heats the majority of their campus buildings. They have over $800,000 in fuel savings per year, and they generate about 4 million kilowatt hours of electricity from this facility that then feeds back in. One of the things you need when you're going to have combined heat and power is a relatively high electric demand that goes with your relatively high heat loads. in our particular climate. And so, for instance, when Cortland looked at this, the balance between our heat demand and our electric demand was not such that this looked terribly attractive. For others, this will look very attractive. Cornell uses combined heat and power with natural gas currently. Middlebury shows that you can do that with biomass. They have a 12-year payback comparable to what Cortland found for its smaller heat pump system, and a similar rate of return just north of 8.5%. So the last thing we'll talk about is some of those economic risks that we have avoided building into our baseline model, but are important to know. So the first is to note that the energy variability between natural gas and electricity over the last couple of decades has not been the same. So the red line here is showing the year-to-year price swings in electricity. And you can see that generally it's swung no more than 5% up or 5% down in any given year. The blue line shows you natural gas's variability. And if you're a commercial real estate owner, those higher variable costs are going to be something that is a real cost to you, because here you are in 1 year, 2 years later, you're projected up 20% over what you were that previous 2 years, then huge drops, another big rise as you go forward. The less consistent price has an economic cost to you. And in fact, if you couple the lower variability of electricity with the lower energy use, what you would find is about 2 to 3 times less swing in your annual O&M costs if you went with the air and ground source heat pumps. Now, if you also coupled that to the solar that Melissa mentioned, that curve would go flat, because you would have locked in your price and you would know every year exactly what that price would be, and you would have either no escalation or a fixed escalation at usually 2% or 2.5% for those PPA prices. You would know exactly what you were going to pay every single year. This also assumes only that low baseline increase in cost for natural gas. So the red line is what we have used in all of our calculations here. It's the EIA, the Energy Information Administration, their lowest cost. This is the government agency that projects these costs forward. The highest government estimate we found follows that green track. And this assumes questions like, will natural gas be exported as liquefied natural gas from the United States? How much natural gas is there, in fact, in the ground? This is the more conservative estimate, the low costs. This is what it could be. And if you look out over that same 30 years, there's about a 60% average difference in price between the low cost and the high cost pieces. So when we talk about price risk and energy security, natural gas actually has quite a risk shadow. It's more variable year to year, and it has a much higher uncertainty going forward in terms of what those ultimate costs can be. That's why when we talk about this, we often say that natural gas is perhaps better discussed as energy familiarity than energy security. So the sort of punchline, right, is that if you want a more resilient system, the best way that you can do this is to use less energy. Every BTU that you don't have to generate, you don't have to consume, is one that you can save. And if we couple that lower energy use with a less volatile energy price like electricity, you can actually now begin to build a much more resilient energy system. So I'm going to turn it over to Gay to wrap us up, and then we can have time for Q&A.
Thanks, Brice.